Photoelectric effect and dual nature of matter and radiations. What is meant by photon? A packet or bundle of energy is called a photon. Energy of a photon is E is equal to h nu. Since nu is equal to c by lambda, we get E is equal to hc by lambda because c is equal to nu lambda. From this relation we can get nu is equal to c by lambda. Where h is Planck's constant, nu is the frequency of the radiation of photon, c is the speed of light, that is electromagnetic wave, and lambda is the wavelength. What are the properties of photons? A photon travels at a speed of light c in vacuum, that is 3 × 10⁸ meter per second. It has zero rest mass, that is the photon cannot exist at rest. The kinetic mass of a photon is m equal to E by c square, which is equal to h by c lambda. The momentum of a photon is P is equal to E by c, this is equal to h by lambda. Photons travel in a straight line. The energy of photon depends upon frequency of the photon. So the energy of the photon does not change when photon travels from one medium to another. The length of the photon changes in different media. So velocity of a photon is different in different media. Photons are electrically neutral. Photons may show diffraction under given conditions. Photons are not deviated by magnetic and electric fields. What is meant by photoelectric effect? The phenomenon of emission of electrons from mainly metal surfaces exposed to light energy such as X-rays, gamma rays, ultraviolet rays, visible light, and even infrared rays of suitable frequency is known as photoelectric effect. The electrons emitted by this effect are called photoelectrons. The current constituted by a photoelectron is known as photoelectric current. Note, non-metals also show photoelectric effect. Liquids and gases also show this effect, but to limited extent. For metals, if a ultraviolet is incident on it, photoelectrons will be emitted from the metal surface. Metals other than alkali metals, visible light incident means there is no photoelectrons emitted from it, from this alkali metal. For alkali metals, visible light is instant means we can get photoelectrons. Metals other than alkali metals, we cannot able to get photoelectrons. Experiment setup to study photoelectric effect. Consider a quartz bulb which has a window. Consider a cathode, this is negative electrode. Consider anode, which is a positive electrode. Consider key and with rheostat and battery arrangement. Micrometer is to find the current through the circuit. Voltmeter is connected to find out the potential difference, that is voltage. Here C is metallic cathode, A is metallic anode, W is quartz window. If ultraviolet is incident on the cathode, if circuit is completed, so that we can get electrons, that is photoelectrons from the cathode towards anode, so that we can get the ammeter reading. Here photoelectrons or in violet color. Glass transmits only visible and infrared lights but not ultraviolet. Hence quartz, because quartz transmits only ultraviolet, that's why quartz bulbs are used. Light of suitable frequency falls on the metallic cathode. Photoelectrons are emitted. These photoelectrons are attracted towards the positive anode and hence photoelectric current is constituted. Effect of intensity of incident light on photoelectric current. Consider this graph. Along x-axis intensity, along y-axis current in microamperes. Intensity is directly proportional to photoelectric current. That is number of photons emitted from the metal surface in unit time. For a fixed frequency, the photovoltaic current increases linearly with the increase in intensity of incident light. Effect of potential on photovoltaic current. For this graph is like this x-axis, along x-axis anode potential. This potential anode in volts. Current in microamperes. So for particular intensity L1 and for potential intensity L2, we can get two similar graphs starting at the same point. So because of intensity directly proportional to current, it is L1 is less than L2. Or LT is greater than L1. So this is a stopping potential. This point is known as stopping potential. This is saturation current. For a fixed frequency and intensity of incident light, the photoelectric current increases with the increase in positive potential applied to the anode. When all the photons reach the plate A, current becomes maximum and is known as saturation current. When the potential is decreased, current decreases but it does not become zero at zero potential. This is known as stopping potential. This shows that even in the absence of accelerating potential, a few photons manage to reach the plate on their own due to their kinetic energy. When negative potential is applied to the plate A with respect to cathode, photoelectric current becomes zero at a particular value of negative potential called stopping potential or cutoff potential. Intensity of instant light does not affect the stopping. Effect of frequency of incident light on photoelectric current. For a fixed intensity of incident light, the photoelectric current does not depend on the frequency of the incident light, because the photoelectric current simply depends on the number of photoelectrons emitted and is stand on the number of photons incident and not on the energy of photons. Effect of frequency of incident light on stopping potential. Take potential of anode, that is anode potential along x-axis, and the current in microampere along y-axis. This is for threshold frequency 1. This is stopping potential 1, Vs1 is. This is for stopping potential 2, Vs2. For threshold frequency 2, that is nu t is frequency value, maximum frequency. That is nu 2 is greater than nu 1. For those, saturation is same. Hence, for a fixed intensity of incident light, the photoelectric current increases and it is saturated with increase in positive potential. That is positive potential applied to the anode. However, the saturation current is same for different frequencies of the incident lights. When potential is decreased and taken below zero, photoelectric current decreases to zero, but at different stopping potentials for different frequencies. Higher the frequency, higher the stopping potential. That is Vs is directly opposed to frequency. Stopping potential is directly opposed to frequency of incident light. What is mimic threshold frequency? So take frequency along x-axis and stopping potential along y-axis. So it is a linear curve. Graph between stopping potential and frequency does not pass through the origin. It shows that there is a minimum value of frequency called threshold frequency, below which photoelectric emission is not possible. Or this section is consider this section. However, high the density of incident light may be. So below which photoelectric emission is not possible. So below the particular frequency range, photoelectric emission is not possible. However, high the intensity of this light may be. Depends on the nature of the metal emitting photoelectrons. Loss of photoelectric emission. For a given substance, there is some minimum value of frequency of incident light called threshold frequency, below which no photoelectric emission is possible. However, intensity of incident light may be. Number of photoelectrons emitted per second, that is photoelectric current, is directly opposed to the intensity of incident light, provided the frequency is above the threshold frequency. The maximum kinetic energy of the photoelectron is directly proportional to the frequency, provided the frequency is above the threshold frequency. The maximum kinetic energy of the photon electrons is independent of the intensity of the incident light. The process of photoelectric emission is instantaneous, that is, as soon as the photon of suitable frequency falls on the substance, it emits photoelectrons. Photoelectric emission is 1:1, that is, for every photon of suitable frequency, one electron is emitted. Einstein's photoelectric equation. When a photon of energy hν falls on a metal surface, the energy of the photon is absorbed by the electron and is used in two ways. A part of energy is used to overcome the surface barrier and come out of the metal surface. This part of the energy is called work function. That is, Y is equal to h nu naught. Where nu naught is the threshold frequency, h is Planck's constant. The remaining part of energy is used in giving the velocity v to the emitted photoelectron. This is equal to the maximum kinetic energy of the photoelectrons, that is half mv square maximum. Where m is mass of the photon, v max is the maximum velocity. So consider this metal. Photon of hν is incident on the surface. So photoelectrons emitted. Here phi is equal to h nu naught. That is the work function. Phi is equal to h nu naught. Photoelectrons carry the photon is half mv square maximum. According to the law of conservation of energy, hν is equal to phi plus half mv square max. That is, part of the energy is in the form of work function. Remaining part of the energy is in the form of kinetic energy of the photoelectron. So one part is used to remove the electron from the surface of the metal. Another part is giving kinetic energy to the photon. That is the kinetic energy of the photons. So substitute the value of phi, h nu naught plus half mv square maximum, or h half mv square is equal to mv square maximum equal to h nu minus h nu naught. Since h nu equal to h nu naught plus half mv square maximum, or half mv square maximum equal to h nu minus h nu naught. If we take h common, means we can get h of nu minus nu naught. Previous laws of photoelectric emission based on Einstein's photoelectric equation. Half mv square maximum equal to h of nu minus nu naught. If nu is less than nu naught, means then half mv square is negative. This is not possible. Therefore, for photoelectric emission to take place, nu must be greater than threshold frequency. That is, frequency of incident photon must be greater than threshold frequency. Since one photon emits one electron, so number of photon electrons emitted per second is directly proportional to the intensity, that is incident light. It is clear that half m square maximum is proportional to frequency, as h and nu naught are constant. This shows that kinetic energy of the photon electrons is directly proportional to the frequency of the incident light. Photoelectric emission is due to collision between a photon and an electron. As such, there cannot be any significant time lag between the incidence of photon and the emission of photoelectron. That is, the process is instantaneous. It is found that delay is only 10 power minus 8 seconds. Application of photoelectric effect: automatic fire alarm, automatic burglar alarm, scanners in television transmission, and reproduction of sound in cinema, film, in paper industry to measure the thickness of paper, to locate flaws or holes in the finished goods, in astronomy, to determine capacity of solids and liquids, automatic switching of street lights, to control the temperature of furnace, photometry, beauty meter to measure the fair complexion of skin, light meter is used in cinema industry to check the light, photoelectric sorting, photo counting, meteorology. Dual nature of radiation and matter. Wave theory of electromagnetic radiations explain the phenomenon of interference, diffraction, and polarization. On the other hand, quantum theory of electromagnetic radiation successfully explained the photoelectric effect, Compton effect, black body radiations, X-ray spectra, etc. Thus, radiations have dual nature, that is, wave as well as particle nature. Louis de Broglie suggested that the particles like electrons, protons, neutrons, etc. have also dual nature. That is, they also can have particle as well as wave nature. In no experiment, matter exists both as a particle and as a wave simultaneously. It is either the one or the other aspect. That is, the two aspects are complementary to each other. His suggestion was based on the nature loves symmetry. The universe is made of particles and radiations, and both entities must be symmetrical. De Broglie wave. So consider this de Broglie wave, wavelength shown in the figure. According to de Broglie, a moving material particle can be associated with a wave. That is, a wave can guide the motion of the particle. Wave associated with the moving material particle are known as de Broglie waves or matter waves. Expression for de Broglie wave. According to quantum theory, the energy of the photon is equal to h nu, which is also equal to hc by lambda. Since c equal to nu lambda. According to Einstein's theory, the energy of the photon is equal to mc square. So left hand sides are equal, so that we can get a lambda equal to h by mc, or lambda equal to h by p equal to mc. So if instead a photon we have material particle of mass m having velocity v, means we can get lambda equal to h by mv, since c is replaced by v, that is other than speed of light. This is the expression for de Broglie wavelength. Conclusion: lambda equal to h by mv. De Broglie wavelength is inversely proportional to the velocity of the particle. If the particle moves faster, wavelength will be smaller and vice versa. If particle is at rest, then the de Broglie wavelength is infinite. Suppose we substituting is equal to 0, means we can get anything by 0 infinity, so hence lambda is infinite. Such a wave cannot be visualized. De Broglie wavelength is inversely proportional to the mass of the particle. The wavelength associated with a heavier particle is smaller than that with a lighter particle. De Broglie wavelength is independent of the charge of the particle. Matter waves, like automatic waves, can travel in vacuum, and hence they are not mechanical waves. Matter waves are not electromagnetic waves because they are not produced by oscillatory charges. Asian German experiment. This is filament. For filament, very small amount of wood supply is collected. C is cathode, E is anode. The entire section is called electron gun. So varying potential level source for cathode negative terminal is connected and for anode positive is connected. So that's nickel crystal. This is crystal lattice is shown in the figure. So if the electron beam, that is electron beam is incident on the crystal lattice, means it can be directed by the detector shown in the figure. So we can move the detector so that we can get the angle of the movement of the detector. So here, if this is the value of theta, means here also we can get the same value of theta. This is angle of phi. The beam of electrons emitted by the electron gun is made to fall on nickel crystal cut along cubical axis at a particular angle. The scattered beam of electron is received by the detector, which can be rotated at any angle. The energy of the incident beam of electrons can be varied by changing the applied voltage to the electron gun. The energy of scattered beam of electrons is found to be maximum. The angle of scattering is 50 degree and the scattering potential is 54 volt. So theta plus theta and 50 equal to, we can get 80 degree, that is theta equal to 65 degree, because theta plus theta means we can get a 2 theta plus 50 equal to 180. So 2 theta equal to 180 minus 50. So 2 theta equal to 130. So theta equal to 65 degree. So for nickel, that is spacing D equal to 0.91 Armstrong. For first principal max, n equal to 1. Electron diffraction is similar to X-ray diffraction. Therefore, Bloch's equation U d sin theta equal to L lambda gives lambda equal to 1.65 Armstrong. You can say incident beam along y-axis and intensity of scattered beam at 44 volt. We can curve like this. Incident beam along y-axis and intensity of scattered beam at 48 volt. The curve is like this. For intensity of scattered beam at 44 volt, we can get maximum. So this is the direction of scattered beam. With y-axis, it makes an angle at 50 degree. For above 54 volts, such as 64 volt, we can get this kind of curve. So according to de Broglie's hypothesis, lambda equal to h by square root of 2 mev or 12.27 Armstrong square root of v. 12.27 Armstrong is nothing but a value of h by square root of 2 me. Therefore, de Broglie wavelength of moving electron at v equal to 54 volt is 1.67 Armstrong, which is in close agreement with 1.65 Armstrong. Intensity versus square root of anode potential. Intensity along y-axis and square root of v along x-axis. We can get this kind of curve. So this is that is dash lines for square root of 54 volt. This is maximum. Diffraction pattern after 100 electrons. Diffraction pattern after 3000 electrons. Diffraction pattern after 70,000 electrons.